Welcome to Chapter 9 of the Raymarching Shader in Unity tutorial by PeerPlay. In this part I will teach you how to add reflection to the signed distance field. We will start by creating a new distance field in which we'll create 8 metaballs that are positioned in a circle based on an angle or degree that we can set. With a smoothness parameter, we can specify how much the balls are blended together. Next, I will show you how to add multiple reflections in the shading. We will use a cube map texture for self-reflecting a skybox on the distance field. To create reflection, we need the reflected vector of each ray on the normals. From that point, we need to do our marching again with the new direction and add the returned results. Calculating reflections is very expensive, and therefore we will set a parameter to specify how many reflections there will be. Reflecting once will show the reflected distance field. Reflecting twice though will only add reflections to the reflected results, so it's a reflection of a reflection. If you find the contents of my tutorials helpful, consider supporting me at Patreon. In doing so, you enable me to continue creating these for my peers, and you get access to the tutorial source files and exclusive content. Special thanks to Andrew Laboy, Devin the Dude, Derek Fegter, Patrick Nugent and Esperdyne. We'll start where we left off in the previous part and add reflection to the shader. But first we'll change the distance field into 8 metaballs that are positioned in a circle, and the spheres will create some nice visible reflections. So let's open up the shader. As we are getting more and more variables in the shader, it's a good habit to organize them for readability. So let me organize them now and remove the variables we used for our previous distance field. Now with these variables organized, let's add some variables underneath the SDF for the public variables that we want to use for our signed distance field. And to create our circle of smooth spheres, we need 3 different variables. The first one is a uniform float4, which we'll call the sphere. And this holds the position and the radius of the sphere. Now the next variable we'll need is a uniform float, and we'll call this the sphere smooth. And this will tell how much the spheres will blend together. Now the last public variable I want is to set the degree of rotation. So we'll make a float and we'll call this the degree rotate. Now let's scroll down to the distance field, and we can remove the float box sphere, and we can remove these 2 lines and keep the ground in there because we also want to have a ground. Let's start by creating the first sphere. So I'm going to call float sphere is going to be an SD sphere of the position P minus the variable sphere dot xyz, and for its scale we're going to use the sphere dot w. Now we don't just want to spawn one sphere, but we want to spawn 8 of them. So let's create a for loop, and we'll say for int I is 1, because the first one is already the sphere. I is less than 8. I plus plus. And inside the sphere loop we're going to spawn another sphere. So let's copy paste this line. Paste it here, and we're going to call this sphere add. And now each time in the for loop we want to add the sphere add to the sphere using a union operator. But we also want to blend the spheres together, so we're going to use a union smooth operator. And we can see that in the distance function. If we look at the smooth Boolean operators, we can see the op_us, which holds one float, another float, and a float k for the smoothness. So let's implement that. So we're going to say that sphere is going to be the op_us of sphere and sphere add, and we want to do that with the smoothness, so we'll get here the sphere smooth, which is our public variable that we made. And now outside the for loop we need to return the union of the sphere and the ground, so we'll say return the op union of the sphere and ground. Now at this point the distance field will return only one sphere because it creates 8 different spheres on top of each other, because we haven't changed anything to the position here where it spawned. Now what we need to do is we need to rotate the vector p of position around its y-axis. So we need a function to rotate something around its axis. We can do this using this function rotate y. This implementation requires a vector 3 and a degree as input. The calculation of rotations are in radians, but I find degrees easier, so on the first line I'm converting the degrees to radians, then it applies a cosinus and a sinus on the x and z axis, rotating the vector. Now in the distance field we don't need to rotate the first sphere, but we are rotating all the other spheres in the for loop, because this is just the initial sphere. So we need to rotate only p. So we'll type rotate y around p, and we want to rotate it by the degree rotate multiplied by its position in the loop, so multiplied by I. Now that should be all for the distance field. Now let's scroll back to the top because I forgot one semicolon here. And with that in place, let's copy these variables and go to the Raymarch camera to implement these in the camera inspector. Now let's scroll down to the sign distance field. Let's select all of these and paste all the variables from the shader. Now I use copy paste, so we use the same variable names in here as we used in the shader. So now just rename these to a public vector 4. And this is going to be a public float. Now let's send these variables to the shader. Now let's remove all of these. And we're going to set a vector first. So we're going to set the vector sphere of sphere. And we need to set two different floats. Now with that in place, let's save this script and go back to Unity. Now back in Unity, all the variables are set to 0, so let's change these. So let's first increase the sphere size, so we see actually a sphere. Now let's change the Z position of it, and then let's rotate. And now you can see that if I'm rotating it, we'll create all different spheres. And based on its Z position or its X position, the spheres will be on a different position. So let's keep X at 0 and set it to a rate of about 10. And let's do the degree rotation of 45 degrees, so we go all the way around. Let's actually make the Z a little bit smaller, so they're a little bit inside of each other. And now what we can do with the sphere smooth is we can smooth the spheres out. Pretty cool, right? Now that we have the distance field, let's create the reflection. You might have noticed this skybox texture. It's a free cube map texture I found online. Based on a normal direction of our distance field, we will add the result of this cube map as an environment self-reflection. Let's convert this texture into a cube map so we can use it in the shader. So with the texture selected, in the inspector, go to texture shape and select the cube. And at the mapping, we're going to select the 6 frames layout cube environment. Now hit apply. And now we have our cube map. Now let's open up the Raymarch shader. Let's first add the public variables that we need for the reflection. We're going to add 4 different variables for the reflection. First of all, an integer to set the reflection count. We need the reflection intensity, which is the reflection intensity of the sign distance field, the intensity of the environment reflection, which is the cube map, and we have a sampler cube with the name of reflection cube, which implements the cube map into the shader. Now let's immediately add these variables to the Raymarch camera as well. So go to this script, and underneath the ambient occlusion, we're going to implement the reflection variables. So I created here another header for the reflection, and with a range between 0 and 2, we'll have the public integer of the reflection count. So we can set it to either have no reflection, 1 reflection count, or 2 reflections. Then we got a range attribute of a float between 0 and 1 for the reflection intensity, the environment reflection intensity, and a reference to the reflection cube map. And now we'll send these variables in the unrender image to the shader as well. So let's add them. So we'll set the integer, the two floats, and we're going to set the texture reflection cube to the reflection cube. So let's save this script and go back to the shader. Now to implement the reflection, we need to scroll down to the Raymarching. Now at this point, we are only calling this Raymarching once in the frag and apply it to the result of the fixed 4 for the color. Now to make the reflection work, we need to call on the Raymarching multiple times. We will convert the Raymarching function into a boolean. All we want from this function is to know if we hit something, and if we did, what that position is. In the frag, we will then apply the shading based on whether the Raymarching returned a true or a false. Okay, so let's start converting this into a boolean. So we're going to create bool Raymarching, and instead of this fixed 4, we're going to create a bool and we'll call this hit. Now when we're calling on the Raymarching, I want to be able to set the max iterations and a max distance. So we're going to add these variables to this function. So we'll type a float for the max distance. And we want to have an integer, and we'll call this the max iterations. Now let's remove this line, and we're going to use the max iterations into this equation here. And the max distance is going to be this one. Now if we've hit the max distance or the depth buffer, then we want to return a false. So we'll say that hit is false. And then we'll break out of the loop, and we need to return here the hit instead of the result. Now we want this function to do two things. We want it to say whether we've hit something or not, but we also want to get the position, which is P. And to get that position from this Boolean operator, we can use an in-out statement. So we're going to type in-out, and we'll call this a float3 P. And instead of making a new float3p here, we're going to use the p from this function, and we're going to set this to something new. And the way the inout works is that when we call this function, any float3 value that we put into the inout parameter will become the result from this function. Now if we do hit something, normally we would shade it then directly, but we will now just say that hit is true. We can remove the result. And the shading, we're going to do that somewhere else. So let's copy this, remove it from here. We are just setting the hit to true, break hit, and return the hit. Now let's paste the lines that I just copied into the frag. And underneath the result, let's make a few enters and paste it. Now inside this frag, we're going to do the entire reflection statements. Now Raymarching returns a boolean, so this statement of result is not correct anymore, and we're going to remove everything here and just make the fixed 4 result that we can use later. And the next thing we need is a float3, and we'll call this a hit position, and we will send this hit position to the Raymarching function using the in-out slot. So this hit position will become the hit position of the Raymarching. So let's do that now, and we're going to create a boolean, and we'll call this boolean hit, and that is becoming the Raymarching. And for this Raymarching, we're going to use the ray origin. We need to send the ray direction. We also need to send the depth. Then we need to send the max distance and max iterations. So we'll use the max distance of the public variable. And we need to use the max iterations that we've set in the inspector. And as a last one, we need to put in here a float3 that becomes the output of this function. So we'll use the hit position here. So now when this statement runs, this hit position becomes the output of P. Now based on whether we've hit something or not, we want to do the shading. So we're going to create an if statement, and we're going to say if hit is true, then we want to do the shading. So let's use these lines inside here. And then we can set an else statement. So if we've missed something, so the else is for a miss, and this one is for a hit. Now in the frag we don't have a P, but we do have the hit position, so we're going to get the normal from the hit position. And we'll do the shading on the hit position as well. And then we'll say that the result is becoming the result of shading, so we'll say fixed for S1 because we wanted to show it. And if we miss, then we just want to set the result to become a fixed for of 0, 0, 0, 0. At this point we have the exact same thing working as we had before. So let's now start by implementing the reflection, and we're going to start by the self-reflection of the cube map. So we're going to say result plus is a fixed for, and we want to look up the result from the cube map, so we can use here text cube with capitals. And first we need to say which cube map we have, so we want to get the reflection cube. And now we need to have a normal direction, and that is N. And we want to get its RGB values. Now we're going to multiply this by the environment reflection intensity, and we're going to multiply that by the reflection intensity. And the fourth value will stay at 0 because we don't want to add anything to the blending between the shader and the Unity environment. Now let's see what this looks like in Unity. So let's save the shader and go back to Unity. Now we need to set these variables a little bit higher. So let's set the intensity to 1 and the environment reflection intensity. Once I set this higher, you can see this on the distance field reflected. And now you can see the cube map based on the normals of the signed distance field is reflected. But this is just self-reflection. It doesn't reflect anything of the distance field around it yet. So once we've made a hit, we want to start doing the reflection. So I'm going to type reflection here. Now reflection is very expensive on the graphics card because we have to do the entire Raymarching again. So based on the reflection count that we're going to set, we want to either do the reflection or not. So let's create an if statement. And if we have set the reflection count to something higher than 0, then we want to do the reflection. Now what we need to do is we need to set the ray direction and the ray origin to a new position. So we're going to say ray direction is, and the new direction is becoming the reflection of its current ray direction by the normal. So we're going to use the reflect, and we want to reflect its current ray direction by the normal. And we're going to normalize this as well. So normalize around this. And now we have the normalized ray direction of the reflection. Now in the previous Raymarching, the ray origin was the world space camera pos, but now we want to set the ray origin to become the position of the hit position from the previous Raymarching. So we're going to say ray origin is the hit position, and we want to start our Raymarching not on this position, but we want to nudge this pause a little bit. So what we can do is we can say plus the ray direction multiplied by 0.01. Now with these calculated, we can run our Raymarching again. So let's select everything from hit and paste it here. Now pay attention because we don't need to use the depth buffer in our reflection. So I'm just going to set the depth buffer equal to the max distance, so it's kind of ignored. And for the reflection, we don't need as much detail as we had for the first Raymarching, so we're going to divide this by 2. So max distance multiplied by 0.5. Any max iteration is an integer, so we can't multiply it by 0.5, so we're going to divide this by 2. So we're going to use twice as less iterations as we had for the first one. Now this boolean will tell us whether we've hit something or not, so we can do a new if statement, and we can say if we've hit something, then we want to do something. And we don't need an else statement here, because if we haven't hit anything, we don't have to add anything to the result. So if we did have a hit, Then we're going to do the shading again. So let's copy paste these lines. So we're going to calculate the normal and we're going to do the shading. And now we can add this to the result. So we're going to say result plus is a fixed 4 of S multiplied by the reflection intensity. And for the alpha, we'll use 0. And now for the second reflection, we can basically do the same thing. So we'll say if the reflection count is above 1, then we're gonna get the new ray direction and ray origin. So let's copy paste these lines. We also want to do a new hit check. So let's copy this line as well. And instead of dividing this by 2, we're gonna divide this by 4. So multiply it by 0.25 and divide this by 4. Now if this has a hit, so if hit, then we'll do the same thing as we've done here. So let's copy paste these. And we're going to divide the reflection intensity by 2 of the second reflection. So multiply by 0.5. Now that should be all for implementing the reflection into the shader. So let's save this script and go back to Unity. So now let's have a look at the reflection. Let me close the game window, make this a little bit bigger. So we have our scene here. Let me set the reflection count to 1 because it's now not reflecting anything. And now you can see the reflection. Pretty cool because each of these spheres showing all the other spheres around. But we can also do a second reflection count. And now you can see that the reflection of these reflections are reflected back. So by setting the reflection intensity higher or lower, we can get some different results, of course. Well, let's change the size of this a little bit. Let's actually add some shadow as well to the scene. So a little bit more intensity. Set the penumbra a little bit lower. The ambient occlusion. This looks pretty cool already, right? Now at this point, we only have one color for the entire scene. This becomes a lot more cool when we add multiple color support to the shader. We will do that in the next and final chapter of this free tutorial series. Hopefully, I will then have found my voice again. After that, I will continue with advanced Raymarching subjects exclusively for patrons on my Patreon. If you found this tutorial helpful, feel free to share this video with your peers. To stay updated to new released parts, subscribe to the channel and turn the notifications on. Happy coding!